All right, we get to one of my favorite tests. It does a lot of homework for us. It's called the limit comparison test. It's super useful to us, right? So what it does is it takes two series, one you want to find out about, one you already know about, and it does a ratio of the terms and looks at the limit as it goes to infinity. That sounds funky, but the way I try to describe this is when you have a series that is converging, the terms have to go to zero. But if the terms don't, for example, so consider this series down here. I'm going to write down here for a little bit. So I have a series 1 over n, and that's equal to 1 plus 1/2 plus 1/3. And you're supposed to shout out that that is the harmonic series, right? And you're supposed to also shout out, it diverges. It's true. But if we look at another P series, 1 over n squared, we get 1 plus 1/4 plus 1/9 plus, you know what? What's the difference between these two? This guy converges. He's a P series with P equal to 2, which is greater than 1. So that one. So what's the difference between these guys? There are fractions being added. Why does one converge and one diverge? It's really interesting. I think it's because when you look at the terms here, they go to 0, but they go to 0 more slowly, let's say, than these guys. These guys go quickly enough by the square of n. Out there somewhere is 1/100th, and out there, you know, it's a lot faster. It's the squares. So they go to 0 quickly enough to where you actually go to a sum. Isn't that bizarre? But these guys are too slow. Okay? So when you run the limit comparison test, what you do is you look at the ratio of their terms. And if the ratio of their terms is some sort of finite number, okay, it's not 0 and it's not infinity, then you know that the two series kind of do the same thing. Now, mathematically, what that really means is if we take a look at, say, two series, series A sub n and series B sub n, okay, and they are positive term series, right? All right, and someone had the bright idea to do the following. Then compute the limit as n goes to infinity, and put one on top of the other, and it doesn't matter which, okay, it doesn't matter which one is which, and you compute the limit, whatever it is. Now there's three possibilities. One, the limit is 0. 2, the limit is boundless, it's unbounded, it's divergent to infinity, and the third is equal to some sort of number that's not 0 and it's not infinity, okay? Well, in the top two cases, if you go to 0, there's no conclusion. And the way I look at that is that the bottom series was faster going to 0 than the top series. And so he went to 0 more quickly, or is it no, the top series is faster in this case, because as n goes to infinity, these two guys, L'Hopital, will go to 0 and over 0. In the bottom case, there's also no conclusion, that is, if you go to infinity. Okay, it's the one where you get a limit L, and it's not equal to 0 and it's not equal to infinity, okay, that you have a conclusion that this implies the two series, well, they're like twins. They're going to 0 at the same rate. And so if one converges, the other converges, and if one diverges, the other diverges. So I like to say the two series do the same thing, meaning they both converge, or it could be both diverge. Okay, this is such a handy thing. Right now you're in the dark about it. If you wanted to prove something like this, it's an easy proof. So and the proof would be, and you can read it in the book, but it says let lim as n goes to infinity of an over bn, okay, equals some limit L, okay? Let's say it's not 0 and it's not infinity. So somewhere out in the number line, these guys cluster around L, the ratio of these guys, Okay, I know at the beginning they could be way out there somewhere, but as you go farther along, they get closer. That's what limit means. You get closer and closer. So a person could say, for, well, I'll say, for far enough, I'll say it this way mathematically, for large enough n, we have, well, we're going to close the gate here, call it little m, and close the gate here and call it big M. And so after that, if you go out far enough, they're all going to be within that neighborhood. So that's how math people argue it. We have, since that's the limit, we have m less than an over bn less than capital M. Okay, the ratio's trapped in there because that's its limit. One more move. So that implies m, I'm going to clear fractions. I'm going to multiply everybody by b sub n, that'll clear, and times b sub n. And so we end up with m b sub n is less than a sub n is less than capital M b sub n. And here's the cute part. Here comes our friend Mr. Comparison Test, right? So if series b sub n diverges, that implies series a sub n diverges. How do you see that, Weber? Right here. If the smaller series diverges, the larger one does. But it also says, look at this one. And if series a sub n diverges, that implies series b sub n diverges. And then what you could do is you can go the other way and go, but look, if series b sub n converges, then look at that, then that implies that series a sub n converges, and you just keep on going. Like if a sub n converges, then b sub n converges. They both do the same thing. It's a cute little proof using the comparison test. Now, you don't have to buy into that, but you should really consider doing so, because otherwise this just seems like a magical thing to do. But this is what you can do with this. This is one of my favorites. We're going to attack these one at a time, and this one first. So someone says, determine if this guy converges or diverges. I love to run these. It's so simple after you learn how to do this. I love running these on rational expressions like this guy is. What I do is, I said this on the previous lecture, but what I do is I look at the lead terms and I think it behaves, let's say, behaves like, forget all the other stuff, just series 4. I don't even care about the 4. I'm just going to cancel, see the n squared over n4, I'm going to go straight to it, n squared. Okay, because I'm thinking, well, series n squared over n4 leads me to here. So I'm thinking that that's what it's going to behave like. And you know what? What I would do then is I would say the following. I'm going to run the limit comparison test with series 1 over n squared. And now you have to say this, which is a convergent, right, p series. I hope the more you see this, the better you are at this. Okay. So here we go. You haven't done anything yet. You're going to run the actual thing. So take the limit, first time we've ever done it, n goes to infinity, of one series on top of the other. I don't care which. So it might look like this. 4n squared plus 5n over, this is our series, right? n4 plus 2n squared plus 1. And on top of that, below it would be 1 over n squared. Now I typically skip that and I invert and multiply next, but here's what it looks like. It's equal to the lim as n goes to infinity. Same thing, be patient as we write it again, because I'm instructing you guys, right? Okay, that's that. Invert and multiply n squared over 1. Okay, so that becomes lim. I'm going to multiply through that n, so the denominator's not changing, n to the 4th plus 2n squared plus 1. But upstairs you get 4n to the 4th plus 5n cubed. Okay, if you know how to take horizontal asymptotes, then you know the following. This is my shortcut I allow you guys to do. See right there, lim as n goes to infinity, that limit is 4. Okay? Now here comes the limit comparison test conclusion. You ready? We got a limit. Look, it's not 0. Look, it's not infinity. When that happens, you get to reach your conclusion, and the conclusion is this. That implies series whatever it was. What was it? 4n squared plus 5n all over n to the 4th plus 2n squared plus 1, okay, n to the 4th, etc., converges. Why? Because this series converges. We ran the test. We got non-zero finite number. Therefore, they both do the same thing. Okay? That's how it's done. Let's look at another one. Okay, you can pause and look at that and stare at it, but here comes another one coming at you. This one. I'm going to do it the same way. It's very, very straightforward process. I'm going to circle what I see there, and I think it's like, series 1 over, what is that inside there, a square? N, let me see. Yeah, n square root n squared, which to me, let's simplify the power there. That's 1, that's like, that's like n squared downstairs, isn't it? I didn't expect that to happen. But look at this one also is looking like 1 over n squared. I wish I had a different example, like one that converged or diverged. But you know what? It's the same thing. I'm going to run the limit comparison test. Tell the world I'm doing that. With series 1 over n squared again, which is a convergent piece series. Now remember, what I'm writing down is what you should be writing down when you're doing your own work. So I'm saying, not this part per se. You can skip that part. You go, I can kind of see it. But you want to tell me you're running the limit comparison test. You want to tell me, if you're running that test, then you say, I'm going to compare it to this series. You got to tell me it converges and why it converges. And then you run the limit. Okay, lim as n goes to infinity. Let's see, this is 1 over n square root n squared plus 1. This time I'll write it as divided by 1 over n squared, okay, instead of one on top of the other. So once again, we are going to invert and multiply, and we got n squared over 1, and we're getting this limit. Now this limit here with a radical bugs people, n squared over n square root n squared plus 1. But you can, in my case, in my class, what you can still do is just, since we're dealing with positive numbers, you don't have to worry like in Calc 1 of what is it positive, is it negative. You just look at the powers, and the powers match, don't they? It's n squared over n squared, so this limit actually is 1. Okay, you can do it different ways, but we notice again, it's not 0. And also, it's not infinity. So the two series do the same thing. So that implies our series, which is 1 over n square root n squared plus 1, also, well, what does he do? Converge? This guy also converges QED, and that one's done. You see, I just look at it and I go, it looks like this series, let me run a test. But it's only really good for rationals or quasi-rationals, maybe radical expressions. It's good for those problems. Whenever you see one of those and they say, does it converge or diverge? This is what you do. Now, we got one more example, but there's a surprise to this example. I don't know. Do you see what I would do with this one here? Yeah. If I look here, you could even go, well, it's kind of like 4 over 2 or just 2. You're right. It's almost like adding 2 every time. If you were to look at a bunch of numbers here, way out there, the fractions would be close to 2 that you're adding every time. But you know what? This reminds me that I should run, surprise, did you think of it? The divergence test. Aha, I just threw it in there to be honest. Look, you just go lim as n goes to infinity of this guy. 4n minus 1 over 2n plus 3. It's a different test. This limit is 4 over 2 is 2, which is not 0. That implies the series 4n minus 1 over 2n plus 3 diverges. I didn't use the limit comparison test, did I? I threw that in for free saying, not all rationals. If the rational term doesn't go to zero, it's an easy problem with the divergence test. But as you can see in these previous two problems, that if you ran the limit, you would go to zero because the lower powers are bigger downstairs. The powers are bigger downstairs. Okay, there's a lot of gobbledygook there. It's one of my favorite tests. It's really useful and easy to use. Okay, so you should get on the homework. And obviously, any questions, just email me and we'll talk in class. Okay? There's a quick look at the limit comparison test. It's a goodie. See you in the next one.